Okay, so today we're going to be talking about homework 2, and which uses a hybrid convolutional neural network and deep neural network. It's going to measure performance using k-fold cross-validation, or in my case, stratified k-fold cross-validation. The study is going to explore the combinations, the impact on performance that combinations that include different hyperparameters, overfitting mitigation techniques, feature extraction methods, fine-tuning strategies, pre-trained CNN architectures, and different architectural builds. Those are going to be combined to find out what kind of best performing configurations we can discover, and then analyze how these different design choices interact and impact model performance. All right, so part 1 was just about building a simple versus a complex convolutional neural network. And after some deliberation, I landed on some different hyperparameters for each of these. Starting with the simple CNN, I used a parameter grid and sort of expanded that to try to centralize all of the hyperparameters. I also wanted to keep the parameters consistent across all the models, but changing only one or two things to make sure that we were analyzing specifically the detail that was in question. So to start with, for the simple CNN, I used 8 filters, 16 filters, and 32 filters or kernels in the convolutional layers. I used a learning rate of 0.0001, and then I rescaled, of course. That's not a okay. And then I used 64 batches and 30 epochs. And in the dense layer, I used 128 neurons. So I used Visual Studio Code to organize the functions that I was using. So first, we need to prepare the data for a k-fold split. And for that, we need to use only the training directory of the data set. And we want to create our generators based on the X-train and Y-train labels that we created up here. And then we're going to split our data into the 4 folds, and we're going to use our generators to produce images from a data frame, and we're going to use a class mode of categorical, and we're going to put those into a tuple so that we can pass that to a generators list, and each fold will have its own unique training and validation generator. And also, we need to make sure somewhere in here there's a reset weights function. So between each fold, we need to reset the weights and make sure that the next fold is not doesn't have weights from the previous fold, because the point is to reduce noise from that's unique to a particular run, or strange, or a quirk of a particular run, and take the averages of the 4 folds to have a bigger, broader picture of generally how your settings are working. So, for instance, these are all the various folds and their little quirks and individualities between the folds, or within the folds, and then this is the averaged accumulation of all of these values. Okay, so now we're going to build the simple CNN, which is just going to involve our sequential model, and we're going to add our convolution layers, and we're passing in our parameters. Oh. Well, I didn't change something here, but that's neither here nor there. That's, oh, yes, okay, there it is, sorry, okay. Okay, so then we've got the max pooling layers. We're using a 2x2 max pooling technique, which is basically removing every other pixel after that layer and reducing the general size of the image, but it retains the depth, and so it gets deeper and deeper, but with fewer pixels or filters or features that it's looking at. Okay, and then let's see here. Then convolution, max pooling, no max pooling, flatten into a 1D vector so that it can be passed to the dense layer and sorted for classification. So, and then in our dense layer, we use our D1 parameter from the parameter grid, 128 neurons, and we're going to use a ReLU hidden activation function and a softmax, which is used for categorical activation for the final layer. And then compile, and we're going to use the RMS prop learning optimizer, and our learning rate we're going to plop in there. And then, okay, so we're moving on to our complex model, which is basically the same thing, but it just has more layers, more max pooling, and that's it. And then we're going to compare those results. And those results are not there, are down here. So here we've got our complex C DNN, and this is our simple C DNN, and the simple C DNN got just above 70% accuracy, and the complex reached 80% accuracy. Oh, and the difference in the parameters for the complex were that so we were asked to use 4 additional convolution layers. So I started at 32, and I used the doubling rule: 32, 64, 128, 256, 512, 1024, 2048, which are, you know, the powers of 2. And so then for the dense neural network, we're going to use 1024 neurons. We're going to keep the same learning rate. We're going to keep the same loss function. We're going to keep the same rescaling technique. We're going to keep everything else the same, but we're just changing the complexity. So in doing that, we got 70% over here on simple, 80% over here on complex, and we got a more consistent loss score on the simple and a more wildly exaggerated diminishing loss score on, or growing, I guess, loss score on the complex side of things. And, you know, that makes sense because it's probably making connections that are, I mean, it is still producing this greater accuracy, but the loss scores are increasing. So, okay, I am almost out of time. So we're going to do down here is part 2 is going to focus on the various optimization, or the various overfitting mitigation techniques, and that's going to include our augmented C DNN dropout, adding dropout and adding weight decay, and those builds are here. The augmentation was done by just adding a set of parameters to the parameter grid and passing that to the image generator for its parameters. And then when it wasn't in use, I just, did that. So, and then the other two had to have differences in the build of the DNN. So we added different layers here. So this is going to be the dropout layer that's added. And then down here is going to be the decay that's added. And we talk about what those are and what those do in the report. So here's a perspective on the dropout decay and all of them combined, as well as the augmented. And so I guess I'm going to go over this in detail and not have time to go over anything else. I don't know how to do this in 10 minutes. It's impossible. But the complex CDNN is going to be the augmentation had the greatest impact on narrowing achieving the highest accuracy score and narrowing the gap between the training and the validation scores. And it did that on both the loss side of things and the accuracy side of things. So, and then the combined had the best scores overall and the best closeness overall. Well, their scores are fairly similar, but so this one's 79. I determined this one was 81. I determined this one's 82. So it's actually not achieving the best score per se, but it stopped at 30 epochs and the trend is still going upward. So you can imagine that if you continued this, it might reach higher than these that have plateaued and don't have any hope of improving later on. Maybe, but they don't show as much promise. This one as well shows hope of continuing to rise. It doesn't have that straight plateau that you can see in the other models. And that closeness means that the training that the patterns that it's coming that it's creating and the conclusions that it's coming to about those patterns are generalizable, meaning that it is looking at an image and finding things that are actually about the class that's in that image, the class itself, and can be taken out of that particular context and put into a new context, and it can still recognize that whatever that class is trying to represent. So let's just say mountain. So it understands the essence of what a mountain is and can recontextualize that anywhere, whereas when there's this divergence, this big gap referred to as overfitting, it means that the training data it's getting smarter and smarter on, getting more and more capable of generating accurate predictions. But as it does that, those accurate predictions are not producing accurate validation predictions when it looks at new data in new contexts. So the data that it's looking at here, it's basically coming to some kind of conclusion. Maybe it's using something completely irrelevant like image quality. Maybe one of the classes for some reason has a different image quality than the rest of the classes, and that image quality works really well for that particular data set, but when it looks at a new data set, all the images are the same quality, so it no longer has that as a cheat to get to the class, because image quality doesn't have anything to do with a mountain being a mountain. So that would be a really easy example, and I'm way over on time, so I'm just going to briefly just kind of scroll down here and look at the data. We've got the crocodile, the barracuda, the puffin is what I called these because they were just real fun. And here we're experimenting with various combinations, and then here we're trying to hone in on maybe the best combinations that we can get to, at least in the study and the parameters that we have, and the resources that we're looking at. I was only able to get to 92%, which I feel like I was supposed to get. I feel like I was supposed to have a bigger, grander realization about the using the pre-trained model than just improving from 80% to 92%, but I don't know. I don't know what I did to not get there, but hopefully I have at least revealed some of the parts of this exercise by experimenting and looking at all the various dropouts and augmentation, and I did see an improvement in this final layer, and my final score was 92%. There are other tests and trials that were run, in addition to the ones that are listed here that are not that haven't been included. So in all of those, I'm choosing the best representations of these various things. Okay, thank you. Bye bye.